Hi everyone. So what I want to do in the first part of this video is finish off a task that we started in both sections and sort of didn't quite finish all the way, which is uppercasing uh, not a character but a string. And uh, I want to do this in a slightly different way than we did in class. We'll have the code posted for the version of this where we had the .data block, and there was the hello world string, where I wrote the string as ASCII encoded directly there. I want to do something slightly different with the program that I write here, which is I want to be able to interact with this program directly from the command line. So I've named this program uppercase.s, and the goal, I can't do this yet. Right now I don't even have this built, but the goal is that I could say something like uppercase hello, and I'd hit enter, and then it would print out the uppercase version of the string I gave. So that's the goal. I want to set that up as our goal. It's a little more interesting than writing the string directly into our program. And it'll also teach us something interesting, which is whenever we run a program, whether we're running LS or running one of the programs you might have written in past courses you've taken, right? There's all these things that come after the name of the command, right? So we have all this stuff like it's like here, these things, right? These are the command line arguments, right? And uh, they can be any strings that we provide there. Um, for example, in your past homework assignments, you had things like PA2 runner, and then you gave a bunch of things here, and those were the arguments to PA2 runner. And given that programs take in command line arguments and then work with them, and that those command line arguments are strings, it stands to reason that we should be able to find them somewhere in memory in our process when it starts up. Because if our program is going to work with those strings, we ought to be able to see them somewhere. So all I have over in underscore start, under underscore start for now in this program is the little snippet of code we had before that would exit the program cleanly. Oops, I see I have a small mistake here where this I meant to have a 1 here. And I just have this open because I want it to be like an empty program for us to play with so that we can get it started and look around in memory. So let me get this built. And I'm going to call it uppercase.o, uppercase.s. Okay. And I'm going to LD uppercase.o. And like we do, cannot find entry simple start, defaulting to something else. That seems wrong. I definitely wrote start in my file. I think that's probably because I forgot to write .global underscore start. So let's try that again. Awesome. Okay. And now if I run this just to make sure I got that system call right, this should exit cleanly. Okay, so there's no error. All right, so let's get this started up. And remember, our goal is that we can run uppercase hello, and the capital hello will print out. Of course, right now nothing happens. All this program does is exit as soon as it starts up. So I want to show you a couple things. One thing is I keep using this -tui argument to GDB, so I'm going to keep using that. But what I kind of want to do is do something like what I've been doing before, which is pass the name of the executable to GDB. But I also want to pass some arguments along with the name of the executable to GDB. Because, for example, I want to be able to see all of the something like hello show up in the output of GDB somewhere in memory. And there's a special flag, we have to give to GDB to do that. So we have to say --args, and now we can give it the name of a executable, and we can give it some command line arguments. Now I could just give it hello, but I'm going to give it something much more recognizable than hello. I'm going to give it a whole bunch of the same character in a row, because we're used to looking for ASCII in our output. So I'm going to give it a whole bunch of A's in a row, because this should help us if we're looking around in memory to see where all of these characters are. Because it should look like this repeating sequence of ASCII encoding of A. So I'm running GDB with this text user interface option. It seems to work pretty well for my terminal setup. Then arg says, I want you to run this command with these command line arguments passed to this command. Okay, so I hit enter. Let's get into a happy layout here. So I'm going to do layout reg, and then I'm going to break on _start, and then I'm going to start. And this thing keeps happening. I'm honestly not sure why. A lot of times when I run GDB and I break on _start, I'm getting this next instruction. I don't actually know why that happens. It's a little bit frustrating that I don't know why it happens, but it's not affecting anything here. I just want to point out that that's happening. I would like it if this had done a break on this line, and it didn't. And I find that a little frustrating. Okay, but this says it's starting this program, and here's the command line arguments to it. And like usual, we see this start up with most things set to 0, CPSR set to this value that we're sort of used to seeing. R7 is set to 1 just because that's what the last instruction did. The PC is set to the current instruction. And I want to draw your attention to one other piece of this that we haven't looked at before, which is this thing called SP. It corresponds to R13. And SP actually has a value in it. It has a value that is a very big number if we were to interpret it as a number. And it turns out that what's at SP is a very interesting memory location. It's the address of memory that has some useful startup information about the process, and it includes references to the command line arguments that were passed in. So I'm going to explore this a little bit. I'm not going to explore everything. I did a little bit of this ahead of time so that I'd know what I'm looking for. I encourage you to explore around this address because there's some interesting, cool stuff you can find there. But what I'm doing is I'm running the examine command on this address, which is in this SP register, or R13. And we're going to see what's there. Okay? So what's here is first the number 2, then a couple of things that look like addresses sort of nearby. And by nearby, I mean they all seem to start with this 7EFFF number. All these seem to start with this 7EFFF number. And so it seems like these are all other addresses pointing to other places, except for this 0 and this 2. This 2 is kind of interesting. I encourage you to restart and rerun the program with different values there. Not different values in this position, but different numbers of command line arguments, and see how this changes. We'll talk about that more in detail. I don't want to dive into that in this video. It's also interesting to see what's at this memory location on your own. But this memory location is particularly interesting for us for what we're doing right now. So I'm going to do another examine of this second memory address that appears when we print this out. So again, I'm going to examine 10 words, but I'm going to look at starting at this address. Okay, so I'm examining 10 words, starting at this address. And that is pretty interesting. Starting at that address, we have a whole bunch of hex 61s in a row. A whole bunch of hex 61s in a row. 1, 2, 3, 4, so 16, 20, 23 of them, followed by a 0, if we think in the little endian order. This 0 is the last byte. So that's 20 of them, which I'm going to guess is lining up with the number of A's we have here, because 61 is the ASCII encoding of lowercase a. So that's pretty interesting. Right? That's pretty interesting. That says this register SP held an address, and 2 words past that address, right? So starting at this C40 ending address and going 2 words past it was another address, and that address held this big list of ASCII characters, or this big all of these ASCII characters that we gave as command line arguments in a row, followed by a 0. It turns out you can play with this more, and we'll talk about this more very soon when we talk about the layout of C functions, which is going to happen also in the next lecture or two. This SP register, this stands for this SP here stands for stack pointer. And we'll talk about why those 2 words together mean so much for the stack pointer as we get in more to C. But from your past programming experience, you know what the stack is, right? It's the place where function calls go. And so this register is holding the address of where that information about the stack is in memory. And it turns out that the command line arguments we give to the program end up being stored in that area of memory on the stack, we could say. So the stack pointer is pointing to a particular address, and at these addresses, we see references to other addresses, and that's finally where the ASCII characters that we passed in on the command line are stored. Okay? So I wanted to show you that because it makes concrete something that, namely command line arguments, that are a little bit magical when you think about the fact that these strings somehow get into our programs. And they're just sitting there in memory at a particular offset.